Hello dear students, our today's topic is the capacitors. In this class we will learn what are the capacitors, how the capacitors are charged and in what condition it is fully charged and how to discharge the capacitor, what is the capacitance of capacitor, and we will also talk about the parallel plate capacitor. We'll find the capacitance of a parallel plate capacitor in different cases, that is with and without dielectric medium between the plates. So to start with, let us see what are the capacitors. Capacitors are the devices that store electrical charge, and it is used in variety of electric circuits like to tune the frequency of radio receiver. It is used as a filter in power supply and as energy storing device in electronic flash unit. And what the capacitors are. Capacitor is an isolated system of two conducting bodies that are separated by some distance in space, and these conductors, they may be of any shape or size. Let us here see the two conductors A and B having charges plus Q and minus Q. These charges on these conductors, this plus Q charge on conductor A, it distributes itself in a way that the surface of the conductor becomes equipotential, that is, the potential at every point on its surface is constant. Let it be VA, and on this plate is VB. And we know that the potential difference, these these conductors having charges, they create electric field around them, and the line integral of the potential difference between these two conductors is the negative, that is potential difference of VB minus VA is the negative of the line integral of electric field between any points on these two conductors, and these conductors are called the plates of the capacitor. So capacitor is an isolated system of two conducting bodies of any shape and size separated by some distance, and these conductors are called the plates of the capacitor. And let us see how the capacitors are charged. So here the two plates of the capacitor, suppose this plate A and plate B, they are connected through a battery. Plate A is connected to the positive terminal of the battery and B is to the negative terminal of the battery. As A is connected to the positive terminal, so what would happen? This is a conductor and it is ready to give the electron. So electrons are pulled by this positive terminal of the battery and leaving this plate A to the positive potential. This where electrons are pulled from this plate by the positive terminal of the battery, this plate will acquire a positive charge. That is, here on this plate there is a deficiency of electron, and negative terminal of the battery will push the electron to this plate B, and these electrons are getting accumulated on this plate B, so this plate becomes negatively charged because on plate A there is a deficiency of electrons, and on plate B there is a excess of electrons. So plate A acquire positive charge and plate B acquire negative charge. That means with the help of this battery, the electrons are transferred from plate A to plate B. If one electron is transferred from plate A to plate B, A will acquire a charge of plus E and B will acquire a charge of minus E. And if 10 electrons are transferred from plate A, So it means what? It means that the plate A will acquire a charge of plus 10e and B will acquire a charge of minus 10e. So during this process, as this is the charging of the capacitor. So during the charging process, more and more electrons reach to the positive terminal of the battery, and positive charge on this plate goes on increasing, and as a result, negative charge on this plate B. So during the charging process, a point comes when all the available electrons from plate A, they are transferred to the plate B, and at that stage the plate A will have maximum positive charge, that it be plus Q, and B will have maximum negative charge. If we remove this battery, we are left with these two plates having charges plus Q and minus Q. Since these plates are separated by some insulating material, and these charges, they remain on the plate, that is the electrons, due to the insulating medium around it. These electrons remains on this plate. That means there is a on this plate deficiency of electron and excess of electron. So in this way we can store a charge. That is, capacitor is a system of two conductors that can store a charge. Now with the help of this battery, we were able to store the charge on these two plates, which are equal in magnitude and opposite in nature. This is a fully charged capacitor. So fully charged capacitor. Now what happens if we connect this charged capacitor having charge plus Q and minus Q? Then what would happen? These electrons get path and they transfer from this plate B to plate A, and suddenly these electrons are transferred and the capacitor get discharged. So when it get discharged, the electrons are transferred from this plate to this plate. So charge on this plate becomes 0, and on this becomes also 0, because electrons, they are transferred from this plate, and it means that now the capacitor is fully discharged. So this is the meaning of the charging and discharging of the body. With the help of a battery, we can store a charge on the conducting plates, and the system, an isolated system of two conducting bodies, are called as the capacitors. Now the question is, how much charge a capacitor can hold at a given potential difference between its plates. We define this by and that is, what does it mean? It means that what is the capacity of a capacitor, how much charge a capacitor can hold. It depends upon the property of the conductor. That is, what is the capacitance of a capacitor. See, what is the capacitance of a capacitor. To do so, electrical capacitance of a capacitor is the measure of its ability to hold the charge. Let us suppose the two plates, capacitor is having two plates, and one plate is given a charge plus Q and other plate minus Q, and let us suppose that the potential difference between the plates of the capacitor is V. So the capacitance of this capacitor is defined as the ratio of the magnitude of charge on either plate to the potential difference between its plates. Capacitance is defined as this ratio, Q by V. Q is the magnitude of the charge on either plate, and V is the potential difference between the plates of the capacitor. That is, Q is equal to CV, where this C is a proportionality constant called capacitance of the capacitor. From this equation, if V is equal to, that is the potential difference, which is also known as in common language as the voltage, if the voltage between the plate is 1 volt, then C is equal to Q. That is the capacitance of the capacitor. It is defined as the amount of charge in coulomb necessary to increase a potential difference between the plates by 1 volt. That is, capacitance is the charge on the capacitor when the potential difference between the plates is unity. It is a charge, it is a charge on, that is the capacitance is the charge on the capacitor when potential difference between the plates is unity, and SI unit of the capacitor is farad. Farad is the SI unit of capacitor, denoted by the symbol F in the honor of scientist Faraday. And farad is enormously large unit because the coulomb is a very big unit of charge. So more practical unit of capacitor is microfarad or picofarad. And picofarad, 1 microfarad is 10 to the power minus 6 farad, and 1 picofarad is 10 to the power minus 12 farad. So this is how we define the capacitance of the capacitor. It is the measure of its ability to hold the charge, and defined as the ratio of magnitude of the charge on either plate to the potential difference between the plates, and its SI unit is farad. And this capacitance of the capacitor, it it doesn't depend upon the Q minus Q. It doesn't depend upon, it is the property of the conductor. Capacitance is the property of the conductor. It doesn't depend upon how much charge is stored at a given potential difference. It depends upon the dimensions of the plates of the capacitor, and what is the dielectric medium between its plate, and separation between the plates. Now we are going to find the capacitance of, we see that the capacitance of a parallel plate capacitor. And parallel plate capacitor, if the conductors are plane conductors, the capacitor is said to be parallel plate capacitor. If it is spherical in shape, called spherical capacitor, and if cylindrical in shape, called cylindrical capacitor. Now we are going to find the capacitance of a parallel plate capacitor without any dielectric medium between the plates, and we will see that the capacitance depends upon the dimensions of the plate, and separation between the plate, and dielectric medium between the plates. It doesn't depend upon the charge on the capacitor and the potential difference between the plates. So for this, let's consider two plates having plate area A and charge Q. Upper plate is given charge plus Q, and the lower plate is given charge minus Q, and these two plates are separated by a distance R. So let's consider two plates of plate area A and plate separation D. Plus Q charge is given to the upper plate and minus Q to the lower plate, and these charges will distribute on the surface of the plate so that the surface become equipotential, or a uniform surface charge density established on the upper and lower plate, plus sigma and minus sigma will establish. Sigma is what? Sigma is the surface charge density. So surface charge density, sigma is the charge per unit area. This upper plate is given a charge plus q and lower plate minus q. So a plus sigma charge density established on the upper plate and minus sigma uniform charge density established on the lower plate. Now this is the cross-sectional view of the parallel plate capacitor with plate area A and plate separation D. Plus q charge is given to the upper plate and minus q to the lower plate. Now, according to Gauss's theorem, the field outside the plate is zero. It was discussed in the previous class in detail that field outside the plate is zero, while in between the plate the field is given as E naught as sigma upon epsilon naught, okay, according to Gauss's theorem. And we have discussed this case while discussing the application of Gauss's theorem. We have done this problem that when two plates having equal and opposite charges, field outside the plate is zero and inside is sigma upon epsilon naught, where sigma is the surface charge density. Now if the separation between the plate is small, then in comparison to the dimensions of the plate, then electric field between the plate is uniform with some deviation from uniformity at the edges. That is, the field lines between the plates are parallel and equi-spaced, showing uniform electric field, and with some distorted line at the edges, and which is called as the fringing effect. Fringing effect, and this can be neglected if the square of the separation between the plate is very less than a. If the separation is small in comparison to the dimension of the plate, the electric field will be uniform with some deviation from uniformity at the edges, and the field lines are parallel, evenly spaced with some distortion at the edges, and this effect is called fringing effect, and this can be ignored if d square is very less than a. So from Gauss's law, uniform field inside, that is within the plate, is sigma by epsilon naught. If W amount of work is done in taking a charge q naught from upper plate to the lower plate, then W will be given as, we know that work done is force which is q naught E. Just a minute, the field is here, suppose we represent this field by A. Q naught E and force into distance d. If q naught, a positive discharge, is taken from this upper plate to the upper plate to the lower plate, a work will be done as q naught E d, and this implies that W by q naught is E d, and by definition, what is this? This is the potential difference. Work done per unit charge in taking from one point to the other point gives the potential difference between the 2 points. So the potential difference between the plates V is E D, where E is the electric field between the plates and D is the separation. Now put this value of E here. So V is equal to sigma upon epsilon naught D, and sigma is charge per unit area, that is Q by A epsilon naught D, or this implies that V is equal to Q by A epsilon naught D, and this implies that if uh, Q by V, this implies Q by V as A epsilon naught by D. And what is this? By definition, this ratio is the capacitance of the capacitor. That is, the capacitance of this parallel plate capacitor is A epsilon naught by D. So from this expression, it is clear that the capacitance of a capacitor doesn't depend upon the charges on its plate and potential difference between the plates, but it depends upon the dimensions of the plate, separation between the plate, and dielectric medium between the plates. Here epsilon naught is the permittivity of free space or vacuum. So this is the expression for the capacitance of a parallel plate capacitor having plate area A and plate separation D without any medium between its plate. Now we'll find the capacitance of parallel plate capacitor when some dielectric material is inserted between the plates. Let us see how the capacitance of the capacitor get changed when a dielectric medium is placed between the plates of the capacitor. That is, we are going to find out the capacitance of parallel plate capacitor with dielectric medium between its plates. Let us see here a capacitor, parallel plate capacitor with plate area A and plate separation D. When there is no medium between the plates, let us suppose the capacitance of the parallel plate capacitor is C0. Let C A is the area of the plate. Let's consider a capacitor with plate area A and plate separation D. When there is and C0 is the capacitance when or capacitance of the capacitance of the capacitor with no medium between its plate. No medium between its plate. So it is given as we have derived earlier, the capacitance of parallel plate capacitor without any medium between its plate epsilon naught A by D. When a dielectric slab of thickness D, which is less than D, is introduced between the plates of the capacitor, let us see what happened to the dielectric. As it was discussed in the previous class in detail, that what happened when a dielectric material is placed in electric field. When dielectric material is placed in electric field, here this upper plate is having charge plus Q and lower minus Q. So due to these charges, there is an electric field, suppose E0, between the plates of the capacitor whose direction is from this upper plate to the lower plate, here shown by these arrows. When a dielectric slab is placed in between the plates, what happened? The dielectric get polarized in direction of the field. That is, polarization vector will be induced in direction same as it get polarized. The dielectric get polarized with dipole moment whose direction is same as that of electric field E naught, because due to this polarization, negative induced charges will appear on the this side and positive on that side. So in this way, this induces that means these induced charges, they set up an electric field EP whose direction is opposite to, from positive to negative charge, that is whose direction is opposite to that of E naught. So in this way, the field inside the dielectric get modified. The net field inside the dielectric is E naught minus EP. E naught is the field when there is no dielectric. When dielectric is placed between the plates, what happen? Dielectric get polarized and the field is modified. It get polarized in direction of the electric field E naught, and the field get modified, that is the net field inside the dielectric is not E naught, but it is now E naught minus EP. And E naught minus EP. And we know that the dielectric constant of the material, the ratio of the field in which dielectric is placed and the net field inside the dielectric is called the dielectric constant. Here K is the dielectric constant, dielectric constant of this dielectric medium. So this implies that E is equal to E naught by K. Means what? It means that when a dielectric slab is placed in electric field, the field inside the dielectric get reduced by a factor of K. That is, inside the field, sorry, inside the dielectric, the field is E naught by K. E naught is the field outside the dielectric, and E is the inside dielectric, which is E naught by K. So now when this slab is of thickness T is introduced between the plates, the potential difference, now the plate is given as, that is, field E is in the space of thickness T, while E naught is in the space of the remaining part, that is of thickness D minus T. D is the separation, T is the thickness of the plate. So potential difference, we know that potential difference is E times D. So it will be for the space of thickness D minus T, field is E naught, and for the dielectric of thickness T, field is E. So potential difference between the plates after introducing the dielectric slab is E naught D minus T plus ET. Now we can write it as E naught T minus T plus E as, write E as E naught by K T, or this implies that potential difference V is E naught, take this E naught outside, D minus T plus T by K, T by K, or E naught is, E naught K be sigma upon epsilon naught D minus T plus T by K, and sigma as Q by A epsilon naught D minus T plus T by K. That is, that V is equal to Q by A epsilon naught d minus t plus t by k, or this implies that q by v as A epsilon naught by d minus t plus t by k, and by definition this ratio is called the capacitance of capacitor. A epsilon naught d minus t plus t by k. This is the capacitance of parallel plate capacitor with a dielectric slab of dielectric constant K and thickness T is introduced between the plates. Now, if the whole space between the plate is filled with the dielectric slab, that means if T becomes equal to D, if the plate is fully filled with a dielectric of dielectric constant K, then what would happen? C is equal to, then C is equal to what? If you put D as T as a D, that is A epsilon naught by D minus D plus D by K, that is C is equal to K times A epsilon naught by D. And what is this? This is the capacitance of parallel plate capacitor with no dielectric medium between the plates. So from here you can say that when a dielectric slab is introduced between the plates of the capacitor, the capacitance of the capacitor increases. Dielectric slab becomes K times the capacitance of the capacitor when the whole space between the plate is filled with the dielectric of dielectric constant K. It becomes the K times the capacitance of the capacitor without any medium between its plate. So on introducing the dielectric medium, so this important point, on introducing the dielectric medium, capacitance of introducing dielectric between the plates dielectric medium, capacitance of the capacitor increases. Let us see what happened to the capacitance of the capacitor if a conducting plate is introduced, conducting plate of thickness, suppose C is thickness T is introduced between the plates of the capacitor. Let us see what will be the capacitance of the parallel plate capacitor. You know that K is what? K is the ratio of E naught to E. If the plate is a conducting plate, we know that inside the conductor field is 0. So for this K becomes infinity, and C is when a conducting slab is introduced between the plates of the capacitors of the capacitor is given as A upon epsilon naught d d minus d upon, that is d minus t plus t by infinity, that is C will become A epsilon naught d minus t if a conducting plate is introduced between the plates. If conducting plate is introduced between the plates, the capacitance of the capacitor of plate area A and separation D is given as C is equal to A epsilon naught d by d. Now if dielectric medium of different thickness and different dielectric constants are introduced, suppose this is of thickness T, E1, K1, T2, K2, T3, K3 is introduced between the plates, then capacitance of the capacitor is given as C is equal to A upon epsilon naught D minus D1 plus, that means if the multiple plates of different thickness and different constants, dielectric constants are introduced between the plates, then how we can write the capacitance of the parallel plate capacitor T1 plus T1 plus T2 plus Tn plus T1 by K1 plus the minus sign, with the minus sign, or write this as T minus this plus T1 by K1 plus T2 by K2 plus Tn by Kn. This is the capacitance of the parallel plate capacitor when the space between the plate is filled by a dielectric of different dielectric constants. So this is all about the capacitors. I hope you understand this, and in the next class we will learn about the combination of capacitors and we'll find the capacitance of the capacitors when different dielectrics are placed between the plates, and the capacitance of multi-plate capacitors. Thank you. Now we are going to end the class.